Pleasant greetings, ladies and gentlemen. My name is Tinotenda Chimbwanda. I'm a student in the Department of Mining and Geological Engineering. And today I'm going to talk about how we can extract water from lunar ice regolith. It goes without saying that humans have always been explorers. Come to think of it, from sailing across vast oceans to stepping foot on the moon, we've always pushed boundaries. And now we are looking beyond, using the moon as a launchpad for deeper space explorations. Many may wonder, why the moon? Why are we going to the moon? Well, friends, the moon holds strategic proposition. And the main reasons why we are going to the moon is because of its microgravity and at the same time, lack of atmosphere, which means we utilize less resources and energy to propel our spacecraft into space. The main resource on the moon that we can find, in my opinion, is water. It not only supports life, but can fuel rockets and even help to build some habitat for civilization that we are going to soon have there. So where do we find water on the moon? We mainly find water trapped in the permanently shadowed regions of the northern parts of the moon, the southern parts of the moon. And studies reveal that we have up to 30% of water in composition of regolith. So the proposed locations for my project are of course, the rims of craters like Shackleton, and also this choice of site for the solar plant was chosen because it's in the vicinity of some of the landing sites that have been proposed for the coming Artemis missions. So looking at current methods, what other people are working on, I found microwave as a common theme amongst many researchers. I have to say that this is a very effective method. It's selective, but in the way that I see it, its strength is also one of its weakness. Its selectivity can hinder it in terms of scalability. And because of that, I believe that's a limitation in as much as it is effective. But when we talk of economies of scale, producing things in bulk, I think it becomes limited. Another method that's quite innovative is the aqua spectrum method. This is innovative in the sense that it uses low energy by proposing to use a process that does excavation and then processing. At the same time, it limits how much we transport waste material. And this is very effective. This is very efficient. But again, that strength is a weakness, because when you have a process like this, it becomes batch process. It means one operation has to wait for the other. So it has to do the scooping and then the processing at the same time, which means that there could be bottlenecks when it comes to production, because one process is dependent on another process. And again, that's a limitation. So what I propose is solar concentration. We can do this at large scale, because we'll be utilizing solar energy, which is a resource that the moon has in quite remarkable abundance. So on the moon, we have up to 1,400 watts per meter squared when it comes to irradiance. And we can harness this more efficiently than we do on Earth, because on the moon, we don't have an atmosphere to absorb the radiation and also to block that radiation. So we can actually have solar energy harnessed efficiently on the moon than on Earth. So this is a schematic presentation of how I propose this to happen. So we look at solar concentration and we concentrate that to produce heat and then use a working fluid to heat the regolith, and that will facilitate direct sublimation of the ice into water vapor. Because of low pressure conditions on Earth, we do not need becoming a liquid, so that will be a direct sublimation. And then I'm going to talk about in a moment about phase change materials. So they will act as a temporary buffer during the lunar night. So this is in essence how a solar concentrator works. So it starts by focusing reflected rays from individual panels onto a central receiver. I say panels, but it's actually reflectors. So we have our reflectors that hits a central receiver, and that central receiver is now having concentrated energy, which then hits the working fluid. And in our case, we then hit the regolith directly. But here we are producing electricity. So you may be wondering, this depends on solar energy, but solar energy, we find it during the day. So what are we going to do during the night? So to sustain operations during the night, I propose to use phase change materials. So phase change materials have got very high latent heat, and that high latent heat allows them to absorb a lot of energy without a change in state, such that when we have the lunar night, it then steadily releases that heat to heat up the regolith. So in this way, we can have sustained operations throughout the cycle of the lunar day-night, so that it's sustained and we produce more of the ice that we need. So this is not just conceptual. This has been done in the past and showed a lot of promise. So there was a study that was done. It's called the Lunar Thermal Ward concept, where lunar regolith was used as a PCM, as a phase change material. So it absorbed sunlight, it absorbed radiation, and during the night, when there was no longer light, it was used to power light rover operations, and then showing that this can be done. Of course, this was done on a small scale, but with more research, it could be done at a larger scale to sustain operations like the ones that I'm discussing here. So I'm cognizant that there are challenges when it comes to the project that I'm proposing, especially when it comes to finding the perfect composite that can last up to 14 Earth days, which is an equivalent of one lunar night. We have seen success here on Earth of PCM that are able to last about 10 days. But to find PCM that can last for 14 days is going to require a lot of research and work. So another challenge that I'm aware of is that on the moon, we have a lot of dust generated, and we should look into how we are going to be cleaning these surfaces. So my research is also going to be focusing on self-cleaning surfaces for these solar panels, so that we do not have them coated with dust, which reduces their efficiency. We could use robots, but that's an added cost. So to actually look into the way to alter chemical composition for chemical cleaning by altering this composition would be a great way to go about it. So I've talked about this, like how my research is going to evolve going further, and also simulations are going to be done to evaluate feasibility of these concepts, and also a cost-benefit analysis comparing with the current methods. With that, I open the floor to discussions, and thank you so much for paying attention.